Let's start with a concept we encounter every day: motion. In physics, motion means a change in the position of an object over time, always measured relative to a reference point. Picture a car moving along a road. Its position changes with time. Now, motion in physics can happen in many ways, but when we study mechanics, we classify motion into two broad types: translational and rotational. In translational motion, think of a person walking in a straight line. Every part of the body moves the same distance at the same time, and there's no spinning involved, it's just moving from one place to another. On the other hand, rotational motion happens when a body spins around a fixed axis. Imagine a spinning top or a wheel turning around its axle. The object still moves, but in circles, with different parts of the object traveling different distances. Today, we'll break down these two kinds of motion in more detail and understand how they differ from each other. Translational motion might be the easier of the two to understand because it's something we see every day. Let's picture a car driving down a straight road. In translational motion, all parts of the object move the same distance in the same amount of time. Now, this motion can happen in two ways. It can be rectilinear, meaning in a straight line, or curvilinear, meaning along a curved path. For example, a car on a straight road moves in rectilinear translational motion, while a roller coaster, as it moves along its track, exhibits curvilinear translational motion. The key thing to remember is that every point on the body moves the same distance in a given time. To mathematically describe translational motion, we use displacement, which is simply the difference between where the object ends up and where it started. The formula for displacement is displacement equals to final position minus initial position. It's as simple as that. Whether straight or curved, this is the basic concept behind translational motion. Now, let's dive into rotational motion, which is a bit more complex. In this type of motion, different parts of the object follow circular paths around a fixed axis. Imagine a ceiling fan or the earth rotating on its axis. Every part of the fan blade moves along a circle, but it's all spinning around the center. The key difference here is that, unlike translational motion, different parts of the object move different distances at different speeds. The points closer to the center move shorter distances, while those farther out travel farther. In rotational motion, all points on the body have the same angular velocity, but their linear velocities differ based on their distance from the center. This means that the angular velocity is the same for every point, but the speed at which the points move depends on how far they are from the center. Angular velocity, omega, is equal to the angle moved, theta, divided by the time taken. This means that angular velocity measures how quickly the angle is changing over time. So, whether it's a spinning wheel or the Earth's rotation, it's all about how the object spins around its center. Let's now take a moment to compare translational and rotational motion more clearly. In translational motion, every point of the object moves the same distance at the same time. So, if you're walking, your entire body shifts the same distance from one point to another, and this distance is measured by displacement. However, in rotational motion, things are different. Here, different points on the object follow circular paths around an axis, so the distance each point travels is not the same. For example, the top of a spinning wheel moves a longer distance than the part of the wheel near the center. In translational motion, we typically use distance, velocity, and acceleration to describe the motion, but for rotational motion, we use different terms: angular displacement, angular velocity, and angular acceleration. Angular velocity, for example, tells us how fast the object is rotating around its axis, and angular acceleration measures how quickly that rotation speed changes. Each of these measures is associated with a different unit, so the key takeaway is that these two types of motion are not only conceptually different but are described using different tools and formulas. Now, let's look at a fascinating case where both translational and rotational motions happen simultaneously. This is called rolling motion. A great example of this is the wheel of a moving bicycle. While the center of the wheel moves forward along the ground, that's translational motion. The wheel itself is also rotating around its axis. What's amazing about rolling motion is that different points on the wheel move at different speeds. The point in contact with the ground is momentarily stationary. It doesn't move relative to the surface, while the top of the wheel is moving the fastest. So, in a way, the wheel's bottom point is at rest, while the top of the wheel is zooming forward. This combination of both translational and rotational motions is key to understanding a variety of movements in the real world, from bicycle wheels to conveyor belts, and even the motion of planets and satellites. To wrap things up, let's briefly summarize what we've learned. Translational motion is when all parts of an object move the same distance in the same time, either in a straight line or along a curve. Rotational motion, on the other hand, happens when different parts of an object move in circular paths around a fixed axis, all while sharing the same angular velocity but having different linear velocities. And when these two types of motion combine, as we saw with the rolling wheel, we get a fascinating blend of both translational and rotational motion. This helps us understand everyday phenomena like the movement of wheels, gears, and even how objects roll down ramps. So, whether we are talking about a car on a straight road or a spinning top, these two fundamental types of motion lay the foundation for how we describe and understand motion in the world around us.